Good morning. So this is lecture 2 for chapter 25, we're going to be using some PowerPoints, and then along with the PowerPoints I've got a number of examples written out. So anyway, let's proceed and see how lecture 2 goes. Some of this stuff is going to be a review of what we saw in lecture 1, so I'm going to run through some of these. This is just the title chapter, Electric Current and Resistance. And we had looked at batteries. We talked quite a bit about batteries. So here's an example of a battery, a chemical reaction run with carbon and zinc electrodes in some sulfuric acid solution, and that will pump electrons away from that positive carbon electrode over to the negative zinc electrode. So the zinc electrode picks up electrons, and at the carbon electrode, probably a hydrogen reaction with the water in solution. But for our purposes, we just want to be aware of how these batteries operate. So again, here's another picture. This probably looks more familiar. This is something like a flashlight. We've got a couple of maybe D batteries in there. At least the one on the left looks kind of like a D battery. And again, what we have is the zinc now is wrapped around the outside, and the positive terminal is still the carbon electrode. So again, what we have is this electron transfer taking place through this conductive paste between the two electrodes. So that's how it becomes a solid battery that you can stuff into a flashlight. All right, we had introduced electric current already, and let's go back and take a look at our definitions. I actually want to start with the middle one. The middle one's actually the official definition. That says, instant by instant, this is an instantaneous formula, current is given by the rate at which charges move past a particular location. Now, if we're going to average the current over a certain amount of time, then we can just take, some amount of charge and divide by some amount of time, and that will give us an average value. If it's direct current, which we talked about, if the current's just staying steady at the same rate, then it doesn't matter which formula we work from. But if the current's varying, and we'll see this as we get into future chapters, we'll see more and more complicated circuitry. And we are going to definitely see circuits where the current is not constant, and we'll need to come back and use the definition in terms of infinitesimals. Now the unit of current is the amp, and the amp is equal to 1 coulomb going by per second. So here's a problem. Example says, here is a measurement of current. It says that a steady current of 2.5 amps is running through a wire, and we let that run for 4 minutes. It says how much charge has gone by during those 4 minutes, and how many electrons would that be? So here's the solution to that. So what we've got here then is starting off just a definition of current and saying, hey, if the current's staying constant, we don't necessarily have to use the derivative version. We can go back and just say, hey, there's a certain amount of charge goes by in a certain amount of time, and we can calculate the charge Q by multiplying the current times the time. So the given information in this problem, 2.5 amps, that's equivalent to 2.50 coulombs going by every second. Let's see, the diagram. So here's the diagram, and to diagram what's going on in that flashlight before is, here are the batteries, that's providing a voltage source, and here's the resistor, that's the light bulb that's going to light up, and then here's a switch, and we turn on the switch, we complete the circuit, and that's going to allow electrons to start moving through the circuit at all locations, and our definition of current is opposite the flow of electrons. So we've got these two people standing at different locations. Someone's going to measure the current here, someone's measuring the current here. How are those two measurements going to be compare? And they're going to be the same thing, right? There's no place in this circuit for electrons to build up. When the electrons start moving, they're going to move at the same rate at all locations. So if I had an ammeter, something that measures electric current, I could put it anywhere in this circuit, it's going to read the same value. There's just one loop. It's a pretty basic circuit. All right, let's see. So in the problem, they wanted us to calculate charge. And so to calculate that, we'll say the charge that goes by one of these observers equals the rate of charge going by times the amount of time that we sit there and wait. And charge is going by at 2.50 coulombs per second. And we waited 4 minutes. So 4 minutes is 240 seconds. And that says a total of 600 coulombs of charge went by. All right. Now, how many electrons is that? So remember, we're measuring the charge in terms of coulombs, but the particles, the charge carriers, are the electrons that are going past our observers. And so to calculate that, we're going to say, well, that total amount of charge that went by is equal to some number of fundamental charges. The little e there, that's, well, it is kind of like an electron, but in this formula, little e represents the fundamental charge. So I can do this. I can say the number of electrons going by would be equal to the total amount of charge divided by the fundamental charge, the charge that each electron carries with it. And when we carry out that calculation, it works out to be, the Coulomb units cancel out, and we ended up with 3.75 10 to the 21 electron. We're expecting a big number, right? Electrons individually carry a tiny, tiny amount of charge with them. And so here's the conversion. I think that's probably the key, is saying each electron corresponds to a charge of 1.60 10 to the minus 19 coulombs. All right, questions on that? Now, also, something else that we looked at in our previous lecture, and that is, well, it's called Ohm's law, but what it states is that the current in a circuit depends on the voltage, and it depends on what the resistance is in the circuit. Now, this is not true for all materials. So, not all materials, I guess we should say, is R is not necessarily a fixed constant value. For copper wiring, for a lot of devices that we build, the resistance is a fixed number. But especially for kind of more modern diodes, transistors, those sorts of semiconductor devices, this formula doesn't work well. The resistance is more complicated. Anyway, for our purposes, we're just going to stick with the idea that resistance is a constant. And so, and here's another restatement of that. What it's saying is we're taking two different types of material. The material shown in the upper graph, as the voltage is turned up, right? So I have some variable voltage source, and I just keep cranking up the voltage. Then what happens is we see that the current goes up linearly with the voltage. Now that's the easy kind of materials to work with, and pretty much that's what we're going to be looking at. In fact, entirely. We're going to be looking at these simpler cases where the current exactly follows the voltage. Down here, again, these are more like semiconductor devices, something like a diode. As you turn up the voltage, the current goes up, increases exponentially with the voltage. So there's a real dependence as far as the resistance. The resistance is quite a bit at first, but then the resistance gets less and less as you turn up the voltage. All right, just be aware that there are these other types of devices out there. Now here, what it's showing is we're getting prepared to start looking at circuits and asking about voltages. Now, we've talked already about getting out our voltmeters and measuring different voltages, and now we want to do that in a circuit, kind of component by component. And what we have here is, here's a resistor, and current is going through in that direction. Now we have to ask ourselves, why is the current going through in that direction? And that's because the E field the electric field within the wire itself is going in that direction. So if the electric field is directed in the direction that the current is currently traveling, that says that the voltage must be dropping off. There must be a voltage drop going from A to B. That's how we refer to it. So that tells me that, if I got current going through a resistor this way, A must be at a higher voltage and B is at a lower voltage. Now remember, we can, in a circuit, we can, the voltages are relative. So we're really talking in terms of how much higher or how much lower. And we can determine how much lower the voltage at point B is compared with A by taking the resistance and multiplying by the current. If we had a voltmeter, let's get out the voltmeters. Now remember, on the voltmeters that we looked at in lab, one of the contacts on the voltmeter said common, and the other one was the variable voltage. So the way we would measure this is, for example, we could hook this up a couple different ways. Since A is at the higher voltage, if I take the common connection on my voltmeter and place it at point B, and then I take my variable volt line and place it here, my voltmeter will read a positive value. So, positive whatever, positive 3.7 volts. If I now take the wires on my voltmeter and switch them, then what's happening is we're measuring B now relative to A. If I take that common line and connect it A, B is going to be at a lower voltage, and now when I connect those wires, it'll tell me a negative value. And again, we saw that in lab. We saw if I've got the voltmeter set to DC, that switching the wires will change the sign plus or minus on the reading. All right. So here's another example. Here's a flashlight. It's got one battery. It's 1.5 volts. Now it says that the flashlight, as we're operating, it has a 1.5 volt battery, and the current going through is measured to be 300 milliamps. They want us to figure out how much resistance is in there. And then a second part of the question is, hey, what if, as the battery gets older and older, the voltage decreases? Now, what happens with the battery is you're running this chemical reaction. As long as there's plenty of surface area where the chemical reaction is happening and the electron transfers can take place, then the voltage should be whatever the voltage is for that particular chemical reaction. But as the reagents within the battery become degraded, it's harder and harder for the electrons to find their way through the battery material. And so you can have a drop in the voltage, especially when you ask a battery to do a lot, right? If you ask the battery to produce a lot of current, the current that it produces is going to depend on how much surface area there is where the reagents inside can react and different compounds can transfer back and forth. All right, so let's take a look. I wrote this one up also. So here we are. Here's the flashlight. Oh, look, it's the very same circuit. It's a battery, it's the light bulb, and then here is the current. We got the current I listed here on, above and below. So the current is taking place, running through this loop that we've got here. And so let's look at the given information. In part A, they said we have a battery 1.5 volts, and the current is at 0.3 amps. Now that's getting written as 300 milliamps, and that's pretty common. In electrical work, we make good use of all the prefixes. So make sure that you're learning the prefixes as you go along. So let's take a look at our standard formulas here. V equals Ri, I is equal to V over R. Let's find out in this problem, they want us to determine what the resistance is. So I get resistance by taking V over I. Now that would mean taking 1.5 volts over 0.300 amps, and a volt divided by an amp gives me an ohm. So that's what that unit is it's that capital omega to tell us how many ohms of resistance we have. And the number we came up with is 5 ohms. So by measuring the voltage, measuring the current, in this, again, a fairly simple circuit right now, we were able to determine how much resistance is in that device. So we plug something into the circuit, do those measurements, and go, oh, this is how much resistance we've got in this particular device, in the resistor itself. Now it says, what happens? We operate this flashlight for a long time, and we find that it's not able to produce 1.5 volts anymore. It's only producing 1.2. It's having a hard time. Well, that doesn't change the properties of the resistor. So the resistor is still possesses the property of resistance, and that's going to be the 5 ohms. So coming back to the same formula, flipping things around, this time solving for I. So this time we'll solve for how much current we're getting. And we're taking the voltage, dividing through by the resistance. Voltage is dropped, resistance is the same, and we're getting 0.240. So as expected, as the voltage drops in our battery, well, the resistance stays the same, current's going to drop. So we're not going to see as much current. Now, I saw the 0.240 ammeter come out of this problem, and I'm thinking, hey, I'll use those prefixes. So I converted that into milliamps. So as the battery became weaker, what we saw here was a reduction in the current from 300 milliamps down to 240 milliamps. All right. So this is also a bit of a review. So here is a resistor, and this is what resistors, if you open up electronic devices around, you're going to see these resistors inside. And they have these different colored bands, and these colored bands are actually pretty prominent. I can actually kind of tell what colors they are. Anyway, just information here for your information. The first digit, second digit, there's a multiplier and a tolerance. And the way that works, the different bands, here's a table from your textbook. And the way this is working is the two numbers are giving you a set of values, a couple of significant figures, and then those get multiplied by some multiplier. That was the third band. And the tolerance. Here it comes down to how carefully manufactured the resistors need to be. If you've got a circuit and the resistance is not so important, then you can buy these variable 20-10% tolerance or uncertainty. So there's kind of the resistors are not being manufactured very carefully. And then these really high precision resistors, if it's got to be within 1% or something really tiny, then they put a different color band on it. So it almost seems like you have to go out of your way to manufacture something that has 20% variability. But anyway, that's again, for your information, not necessarily something you need to, definitely not something you need to memorize. All right, so just some reminders. I hope these aren't clarifications. I hope they're just reminders. Batteries, we're going to treat batteries as having a constant voltage. Batteries are going to be a voltage source for direct current. So that's what a battery's role will be in our circuits. Resistance, we're going to say, is a property of the resistor device that we've placed. And we're going to treat the resistances pretty much as being constant. Don't think there's going to be much exception there. Current, they're just reminding us, could be going in each direction. But in general, it's not a vector. If we have a wire, for example, the current could be traveling in either direction. It's not really three-dimensional. If we had a block of material, we could have what's called a current density. You could have current kind of flowing in different directions three-dimensionally throughout, but for our purposes, currents are just going to have plus or minus values to them. All right, and just another reminder, charge does not get used up. Charge is conserved throughout. The only devices we have seen that can store charge are capacitors, and since even with a capacitor, whatever current's coming in one side matches the current coming out the other side. So when we look at each branch in a circuit, the current will have the same value along that entire branch. So again, set of reminders. Resistivity, the resistance of the devices are going to depend on what it's made out of. That's what we're calling resistivity. And then also it's going to depend on the length, and it's going to depend on the cross-sectional area. So those are the properties or the features of a resistor we're looking at. Here's a table again. This is just, you can refer to this in your textbook. It's listing common materials, conductors, here, and then down below it's listing semiconductors. So things like silicon and germanium, even carbon, can be thought of as kind of a semiconductor. They don't have very good conduction properties, but once you start increasing the voltage, the current can become significant, especially if you've placed impurities in some of those materials. All right, and then copper here, noticing they've got some of the very best electrical conductors. Copper is what we use in most of our wiring in our buildings. Silver is a little bit better in terms of conductivity, but it's expensive. So we don't have silver wires, as far as I know, in our buildings. I have not seen silver wiring being used. Now here's an example. What we've got is we've got a speaker system set up. And what they're saying is, well, here is like a receiver device, and that's going to be taking in the input. They're going to amplify that. Signals are going to be sent out along these wires out to our speakers. Now there's 2 wires along the way, and for the most part, we're going to assume wiring has negligible resistance, but this problem, or this example, is actually looking at the case where we're calculating how much resistance is in the wiring itself. And the numbers say this. They say that the wiring is going to be 20 meters long, but we would like the wiring to have no more than 1/10 of an ohm. We want to keep the resistance really small within the wiring itself. So what they're saying is, what diameter wire would I need? So the idea is, if it's going to be really long, how could we keep the resistance low? And we'll do that by making the wiring very wide. So here is the problem set up on that. Ooh, this circuit's a little different. What we've done in this circuit, we've got a voltage source. Now, that's what's ever driving the speaker. So whatever signal is coming out of my amplifier, there's going to be a voltage difference there. And that's going to drive the current. This time I put in 2 resistors. So there is a speaker, which is going to provide some resistance, and there's the wiring itself, which is going to provide some resistance. So I put those in series. So I've got resistors in series here. And so coming back to our formula for resistance, let's think about how wide the wiring would need to be. That's going to come down to a cross-sectional area. So here's the wire piece right here. I'm thinking, what's the cross-sectional area of that wire? This is the length of it. And then it's made out of copper. So I looked up the value for copper. Copper, it said 16.8, 10 to the minus 19 ohms times meters. And then I'm going to remind myself that the area is pi r squared. I went ahead and used big R for both of these. Now that's an example of where we got to be careful. We got to be careful and go, oh yeah, but I'm using two big R's. I've got to keep those, I got to be aware and not get those two confused. Probably a better method would have not been to use the big R. I went ahead and used standard notation. I'm going to try and keep those straight. So here's the cross-sectional area. Now, I calculated for area first. So looking at that formula, solved for area, and then plugged numbers in. So I plugged these 3 numbers, the length, resistivity, and the total resistance. And what I found was that the area of my wire needs to be at least this value, 3.36, 10 to the minus 6 square meters. Now, remember, everything here is in standard units. So if I'm looking at the cross-sectional area of the wire, which is maybe a few square millimeters, when I calculate this, it's still going to come out in square meters. So I'm not so concerned about the 10 to the minus 6. I'm expecting a really tiny number. And I took that area, divided by pi, and took a square root. So what I'm doing is taking the formula for a circle, the area of a circle, and solving for what the radius would be. The radius here then worked out to be a little past 1 times 10 to the minus 3 millimeters, almost 1. And so that's 1 millimeter. 1 millimeter radius. Now I think the problem asked for diameter. I left this at radius. To get the diameter, I multiply by 2. And so it says that we would need copper wiring that's 2 millimeters in diameter. If I do that, if I have copper wiring, I make it out of copper. I have a diameter of 2 millimeters, and the wiring is 20 meters long. So we're finding out how much resistance there would be in a 20-meter length. Now, if we go back and look at that diagram, there are actually 2 wires leading to the speaker. So, if each of those wires is 20 meters long, then that would say that I've got 0.1 ohm, so that was the total resistance that we were looking at. Ooh, I don't know if I did it. The 0.1 ohm is right here, but I also need, oh, here it is right here. Got it. So the total resistance is 0.1 ohm. That's for a 20-meter length wire. So if I got 20 meters out on both sides, that's going to be twice the resistance. So I would have that 0.1 ohm in each 20-meter length. Or the other possibility is that the wiring, or the speaker wire, is actually only 10 meters long, but it's got 2 conductors inside. And so combined length for the wiring would be the 20 meters. Okay. Now the other item that they ask about, so let's get this second part too. We figured out the diameter of the wiring. They ask us to calculate how much of a voltage drop will there be. So if I come back to this circuit right here, I've got a certain voltage that's driving current through my wiring. That voltage is going to get divided up between the 2 resistors. So some of the voltage drop is going to occur in the speaker, but some of the voltage drop is going to occur in the wiring. So probably we want most of the voltage drop to take place in the speaker. We want to be able to drive those speakers. But we are going to have some of the voltage that goes into the wiring itself. That's not going to be available to the speaker. So to calculate the voltage drop within the wiring itself, we can take R times I. Now that's a little risky because we got to get the right R and we got to get the right I. And so what they told us in the problem is that the resistance of that 20 meters of cabling is going to be 0.1 ohm, and we're going to have 4 amps. So they said we're going to have 4 amps going through the wires, and combining that says that we would have 0.4 volts, or 400 millivolts, of voltage drop occurring in the wires themselves. That voltage is not going to be available for the speakers to operate. Okay. All right, now there's a temperature dependence for materials for resistivity. I'm just going to refer to this formula. I think there's one homework problem. I'm not going to say much other than it's just kind of a plug-in. What you can show is that the resistivity actually goes up with temperature for the common materials. So something like copper wiring, if the temperature goes up significantly, you'll see an increase in resistance. But it's at typical operating temperatures, it's going to be a small effect. All right, here's electric power. We talked about this a bit. We had derived this formula saying that the rate at which energy is being used in a circuit is given by I times V. So, and that I times V can be written as I times IR. So it can be written as I squared times R. It can also be written as V squared over R. So there's different ways we can calculate the power depending on what's given in a particular problem. Here is an example. So we got a car battery, it's 12 volts, and we have a headlight that's rated at 40 watts. Now let's think about this. The headlight really doesn't have a property of 40 watts. The headlight has a property of resistance. It's going to be some number of ohms. Now when you buy a light bulb in a store, they are rated in terms of watts, but they're assuming you're going to plug it into the right voltage. So let's see how this works. Let's remember these numbers. 12 volts for the battery, that's a good number. 40 watts for the light bulb. Ooh, back to this circuit again. This time, let's see. What it's saying is, for this headlight, when we plug it into, the power here is 40 watts. We'll plug that in for the value of P. The voltage is 12 volts. We'll put that in for V in the denominator. And what this says is when we turn this headlight on using our 12 volt battery, we're going to end up with 3.30 amps. And then we can take that one step further and say, well, what is the resistance of this headlight? And to calculate R, I came back to our other formula, V over I, and the numbers worked out to be 3.6 ohms. So you think, oh, that's what they should be telling us on the box. They shouldn't tell us that it's a 40 watt headlight. They should tell us it's a 3.60 ohm, because that's what its intrinsic property is. Let's say we hook it up to a battery with twice as much voltage. If we hook this battery up to twice the voltage, we'll get twice the current. The resistance will be unaffected. We'll get twice the current. If we get twice the voltage and twice the current, we'll get 4 times the power. So hooking it up to a battery with twice the voltage, or a voltage source, will actually make the headlight 4 times brighter. Okay? And we're going to be using energy at 4 times the rate. All right. Now, electric power, let's think about this. Power is the rate at which energy is being produced or being used in a circuit. And electric energy is the kind of the accumulated rate at which we've been using the electricity. So if you have a 100 watt light bulb, what that 100 watt light bulb is saying is, well, 100 watts would be 100 joules per second. So that 100 watt light bulb, plugged in, turned on, is going to be using 100 joules every second. So you turn it on and you start counting the joules, right? 100 joules, 200 joules, 300 joules, 400 joules. When my kids were young, they would leave lights on in the house and would walk in the room and start counting 100 joules, 200 joules, 300 joules. So the idea was, turn the lights off if you're not using them, because the accumulation of just leaving the light on, the amount of energy that's being used, is going to increase as time goes by. Now, in electrical speak, on electric bills from PG&E, instead of working with joules as an amount of energy, they use kilowatt hours. Now, what a kilowatt hour is this? 1 kilowatt hour is an amount of energy. It's equal to using something at 1,000 watts, 1,000 joules per second, for an entire hour. So what you can do is you can always take the power of any device, multiply it by how long it's been left on, and that will give you some number. Well, if you put that in watts and seconds, it'll give you some number of joules. If you put in the kilowatts and the number of hours, it'll tell you how many kilowatt hours it is. So here's the conversion. 1 kilowatt hour is equal to 3.6 million joules, or 3.6 megajoules. So Again, I guess we could all say we're not paying our PG&E bills anymore until you put the energy in joules, which are standard units. Come on, stop using those kilowatt hours. We've already got a perfectly good unit of joules that we can use to report, or megajoules, right? They could charge us by the megajoule instead of by the kilowatt hour. Anyway, that's the conversion. Now, if you pay attention to your PG&E bill, I think electrical energy on there is listed at about 20 cents per kilowatt hour. So about 20 cents per 3.6 million joules. So it turns out it's pretty inexpensive. We actually use an enormous amount of electrical energy, and it's so handy and so convenient. Here's an example. Let's say we have an electric heater. Now it says that this electric heater, it's attached to a 120 volt line. So we plugged this into an outlet, right? And the outlets are 120 volts. Now that's not DC, that's AC. But we can still do the problem if we remember from lecture 1. What we do when we're working with AC is work in terms of these RMS averages. So this 120 volts that represents the voltage of our outlets, that's actually an average voltage. It's averaged over time, and so that's an RMS value. Let's see, it's saying how much would it cost to have this electric heater turned on for 30 days. Now, they've got much cheaper electricity than we have. Their electricity is only 9.2 cents per kilowatt hours, and again, ours is like 20 cents. So, not sure how old these PowerPoints are. Electrical energy has become quite a bit more expensive over the past 10 years. So, electric energy rates have gone up. We are spending more in generating our electricity. Now it says this electric heater has a current of 15 amps. So if you're familiar with amounts of current in household wiring, that's a lot. You could have a fuse or a circuit breaker that actually maxes out at 15 or 20 amps. In my house here, I've got pretty modest electrical panel. There's 5 lines, and each line has a circuit breaker, and the circuit breaker is set at 20 amps. So at 20 amps, it's considered high enough that the wiring could start heating up and possibly cause a fire. So when I moved into my house, the house is built like in 1927, and you could go into the crawl space under the house, and you could just see the wires running back and forth under there, the original wiring. And it's what's called knob and tube wiring, not a big issue here, but you can just see the individual wires running along. And there were quite a few sections where the insulation was falling off pretty much. So over the next few years, I ended up rewiring the whole house and putting in 12 gauge wire, which has a diameter of about 2 millimeters and is rated at higher than 20 amps, but still the circuit breakers for each line in the house is at 20 amps. So this is a lot of power. This is like an electric heat. Something else that takes a lot of energy is like a hair dryer, right? You get those hair dryers to blow dry your hair. You look on those packages and they're like 1700 watts or something. Anyway, let's take a look at this example. Now, we switched out the DC batteries and we put in an AC source. So here's our AC voltage source that's like plugging into an outlet. So the given information here then is, as we were saying, this is VRMS. And what we're going to solve for is current RMS, or actually that was given also. So they gave us the VRMS and current RMS. Now remember, all our formulas work the same way, as long as we include RMS values in the formulas we're using, and then the powers are going to be average powers. And that's what we want. We want to be able to calculate the energy usage using average values for the power. So putting the numbers in, it says the average power here is 1800 watts. So again, this is getting close to maxing out one of these electrical circuits. So we don't want to plug too many other devices into this same plug, maybe none at all, at 1800 watts. Now, we needed to calculate the energy. This right now is the power. And to calculate the energy over time, we'll take that average power, multiply by time. So on average, this electric heater is using 1800 joules per second. And how long was it we left this thing on? Oh, was it 3? It was 3 hours, right? Yeah, that looks like 3 hours. 10,800 seconds, that needed to be up here, I guess. The time we want to leave it on was 3 hours. And so I can multiply those numbers together. That ended up being 19.4 times 10 to the 6 joules, and that's 19.4 megajoules. So that's for leaving the heater on just 3 hours a day. That's all that the heater was turned on. Maybe it turns on and turns off using a thermostat or something. Now, a kilowatt hour is 3.6 megajoules, and I used the PG&E value that I got off of my PG&E bill of 20 cents to find out what the cost was. And so I did the conversion right there. So 20 cents per 3.6 megajoules, and what I ended up with was 108 cents a day. So leaving it on for 3 hours is costing a little over $1 a day. If I do that for a month, it's going to be $30 or something for the month. So it's going to be $30 to leave my my heater, my space heater, turned on 3 hours a day each day for the month. All right, and so that's how you do cost calculations for electric energy. And then we also, along the way, I guess we could have solved for resistance. We never did that. We could have figured out how much resistance we have in the circuit. Looks like 8 ohms, is that what it, anyway. All right, and here's how circuits are set up in a house. So this says from electric company, but let's say this is our electric box outside, and we have these different circuits from the electric box kind of branching out to different parts of the apartment or the home or whatever. We have a circuit breaker here which will fail. If the current gets too high, the circuit breaker will open up and stop current from running through the wires. So what they ask in this problem is to go through and determine the total current drawn by each of the devices. So let's take a look and see what we have here. What we've got is, here are the 2 wires that are running through the house, and what happens is, as there's an electric box right here, there's a junction box, and the wires that we're coming in now are junctioned into 2 wires that power up that outlet. Now if I continue following these 2 wires, here's another junction box, and there's another outlet that it's connected to. So you can see there's a series of 4 junction boxes here, each one with an outlet. So if I'm in a room, like the one right here, I have placed a number of outlets. I've got 1, 2, 3, 4, 5, 6 or 7 outlets. They're all on the same line. So I have to think when I start plugging stuff in, every time I turn something on, that's going to require more current. Everything here has been wired in what's called parallel. So that means that each of these outlets is receiving the full 120 volts. There's 120 volts between these 2 lines coming in. If I get out my voltmeter and measure anything on that line, anything here, it's going to read 120 volts. So here's my electric heater, which looks like the one from the previous problem. That's going to draw 15 amps. Now the other item that worries me right away is this hair dryer. That's going to draw 10 amps right there. So 15 amps that we were given in the previous problem, and here I could take the power and divide by the voltage. A 1200 watt hair dryer in a 120 volt line, that's an additional 10 amps. Between the electric heater and the hair dryer, that's too much. So I can't turn on the heater if I'm going to blow dry my hair. I got to turn the electric heater off, or else plug them into two separate systems, because that would be too much current for these wires. There's a possibility of overheating. Okay, so that's it. Oh, and then in addition, they also have a switch set up for the light bulb. So they've got 4 outlets and the light bulb also. Now that's only 100 watts, so that's less than an amp. That's not so much of a concern. The stereo receiver, 350, that looks like maybe 3 amps here. So 1 amp, 15 amps, 3 amps, 10 amps. It's going to be too many amps for this one line, right? All right, just a reminder, we already looked at alternating current. Well, here we go. Here is the current as a function of time. Now, the way we get a current to be nice and steady and uniform is we power that with a constant voltage device, like a battery. If we have a battery going into a circuit, that maintains a constant voltage. Constant voltages are going to give us the possibility of constant currents. Now, here the current's varying, and the current's varying because the voltage is varying. The generators back at the power plants that are powering up our outlets have voltages that are alternating with time. And the way we run our generators, we generate these really almost perfect sine wave forms, or sine function forms, sine or cosine. And so here are the formulas that they're telling us we can use. Here's a V naught sine omega t, where omega is the frequency. Our electricity here in the United States gets generated at a frequency of 60 hertz. Everybody's agreed. They will generate the electricity, the AC, voltage at 60 hertz. That's how fast we're spinning the generator, 60 times a second. And so the omega value, which is in radians, becomes 377 radians per second. But if we generate the voltage as a sine function, then the current running through our devices also is going to behave like a sine function. Now, when we multiply the voltage and the current together, what we get is a sine squared function, and so the power is always positive. If we have current running back and forth in, say, a light bulb, so I've got current that's powering up my light bulb, the current keeps going back and forth through the light bulb doesn't care, at least an incandescent bulb doesn't care if the power is going back and forth, it still lights up. It still heats up the filament, lights up the bulb. And so what's happening here is we're getting these pulses of power as the current picks up and then drops off. So one of these will be current from current going in one direction. The next pulse will come from the current going in the opposite direction. And they'll just alternate as time goes by. All right, and we went through these in lecture 1, so if you remember, when we carried out the average power, we picked up this factor of 1/2 out front. And what we did with that is we defined it in terms of the IRMS and the VRMSs. So each of those picked up a square root of that 1/2. So the IRMS and the VRMS are lower than the peak values, and they're lower by a factor of 1 over the square root of 2, or 0.707. So that 120 volt number that we talked about with our outlets is actually only 71% of the peak voltage in that line. Here's our hair dryer. Says it's 1,000 watts. That's actually pretty low for a hair dryer. And it's just saying, hey, if we carry this over to, say, somewhere in Europe, now Europe has a different standard. They work with 240 volts in a standard outlet. If we double the voltage, we'll double the current. That'll be 4 times the power. Now, for a hair dryer with a heating element like this, it'll just melt the heating element. It's not built to take 4 times the power. Now, here's kind of the last topic we want to look at in this chapter, is asking about drift speed. So we could say, okay, fine, I've got current going through wires. Is there a way we could actually go in and calculate, on average, how fast are electrons moving in that wiring? And that's what we refer to as drift velocity. So the electrons aren't necessarily moving in a steady forward direction, they're kind of bouncing back and forth. It's just kind of on average that they're making their way through a piece of wiring. Now, a lot of times there's a misconception that, hey, when you turn on that switch, those electrons start moving at near light speed, and that's not true at all. It actually turns out when we go in and we'll do these calculations and see, the electrons are moving really slow typically. If we're keeping the current down to a safe level, the electrons are moving at a really slow speed. Now they've done a bit of a derivation here, but I kind of did my own. So let me move on to the next slide here. And here's a wire, cross-sectional area. Current is going through my wire. And what I want to do is think, okay, I got these electrons. Now the electrons are actually moving the other direction, but I drew the V just thinking in terms of current. Let's say that we section off a little part of that wire and call that length dx. Now it's got a length of dx, but it's got a cross-sectional area of A. And remember, the current can be written down as dq dt. So if I draw that line right there and I stand there and I watch the current go by, I can count how much charge goes by during a certain time interval. That gives me my measurement of current. Now what we can do, and this is kind of an interesting, and I think it's a useful way to start thinking in terms of these infinitesimal values. This can be thought of this process of taking a derivative of q with respect to time, but another way to think about it is during the time interval dt, an amount of charge dq goes by. So what I'm thinking of is that numerator is an amount of charge. It's an amount of charge dq, and that denominator is an amount of time dt, and there's a certain ratio of dq divided by dt, and that tells me what current is. Now, if this is just a pair of variables, I'm just taking a pair of variables and dividing them, what I can do is I can insert other variables into the formula. So what I did was, this kind of an extreme example, but if I take dq dn, where n is the number of electrons, and then I take dn d volume, so that's a little piece of volume over here, and then I take d volume dx and then dx dt, that should be the same expression, because the dn's will cancel, the dv's would cancel, the dx's would cancel, and I've come back to dq dt. Now what I can do is I can go in and ask, well, what is the meaning of each of those ratios? And the charge per number of electrons, that would give me the fundamental charge. That would tell me how much charge is on each one of the electrons. So dq dn, where dn is some number of electrons within that little section, all of these infinitesimals here refer to that little short section of wiring that we're looking at. So however much charge is in there is related to how many electrons there are. And there's going to be some number of electrons per volume. We call that number little n. That's an electron number density. The next ratio, dV over dx, that's actually the cross-sectional area. And I thought I had written it down, but so if I look at that little piece right there, that's got a certain volume to it. So that's a little v, and these are big V's. It's got a volume to it, and the volume of that is dx times whatever the cross-sectional area is. And then finally, dx dt. And what dx dt is saying is during a time interval of dt, that little block of electrons crosses my boundary. So if I'm standing there watching, during the interval of dt, that's how much charge goes by. And that would give me my drift velocity which I'm going to write as little v. So I got this formula now, and it says that the current, the rate at which charge is moving through this wire, depends on how closely packed the electrons are. How many electrons do I have available? What's the cross-section of the wiring? Because if it's a cross-sectional area that's bigger, that's more electrons that are in motion. How fast are the electrons moving, and how much charge do they have on them? Now, to carry out this calculation, what I did up here at the top is I determined how many electrons are available in copper wiring. In a block of copper, how many electrons are there per volume? So copper, it turns out, is element 29. And so each atom of copper has 29 electrons attached to it in some sense. Now, of those 29 electrons, 28 are pretty much locked into place. So they're not available for creating a current. Turns out that in each copper atom, or in a block of copper, there's only one electron per atom, per nucleus, that actually is mobile. It can move around freely. So we're not actually counting the total number of electrons. We're counting how many free electrons there are. How many electrons are available to move from one location to another and create the current that we're hoping to create. So I did this. I looked at the density of copper. I looked at the molar mass of copper. I put in Avogadro's number, and I did a units conversion from meters out of centimeters into meters. Now when I did that and combined all these together and made sure all the units canceled out, what I ended up with was, in a piece of copper, there are 8.49 10 to the 28th atoms for every cubic meter. Now, cubic meters, that's a lot of copper, right? But there's 10 to the 28, or 8.5, 10 to the 28th electrons. Now, since each copper atom has one of its electrons that will help create the current, that means I can use that same number to calculate how many electrons are available. So that's my number for little n, and I can put that in the formula. So what it's saying here is this: the current can be thought of as, depending on how many electrons are available, well, how much charge do the electrons have? I can't do much about that number. The electrons have a fixed amount of charge to them. So these two numbers just come from properties of the electron and the properties of copper. And then it says that the current then is going to depend on the speed of the electrons and the size of the wiring that I have. So if I wire up the house, then the cross-sectional area is also fixed, and that says when the current goes up or down, all of the, everything where there's a current varying in a device comes down to the electrons moving faster or slower. That's the only thing, once I've wired up the house, that's going to be a variable. So I just thought this, let's do this. Let's say that I have some 12 gauge copper wire that I've wired my house with. Turns out that 12 gauge copper wire has a diameter of about 2 millimeters. We talked about this in that earlier problem. That says the cross-sectional area then would be pi r squared, and I don't see if I've written that down anywhere, but that would be 3.14 10 to the minus 6 square meters. Now, let's say that we have electrons moving at 1 millimeter a second, and you're thinking, what? The electrons have got to be moving faster than 1 millimeter a second. If the electrons are only moving at 1 millimeter a second, that's going to take them 1,000 seconds to travel just 1 meter. It's going to take like 20 minutes for an electron, individually following an electron. It's going to take like 20 minutes or something to travel a meter. Are electrons really moving that slow inside wiring? And we can check this and see. Let's see, if we use a number of 1 millimeter per second and we plug into our calculations, it actually says that would create a current of 43 amps. 43 amps is way too big. That's way, well, it's at least, it's more than a factor of 2 larger than what my circuit breakers would allow. So what that says is I can't get the electrons going as fast as 1 millimeter per second. That would be dangerous. That would heat up the wiring unnecessarily. So we actually would have electrons in a wire, even if we've got a high power device, that electric heater we had before with 15 amps. Even that is going to require a speed that's about 1/3 of that. So if I slow that down to like 0.3 millimeters per second, it's going to take like an hour for an electron to get from here and follow 1 meter in my circuit, which is obviously surprising. So it's not that the electrons are moving at breakneck speed here, it's that there's a good number of electrons, and they carry a reasonable amount of charge each. They don't have to travel very fast in order to provide a good amount of current. Now, another thing we got to keep track of here is that this is wiring inside my house. It's not direct current, it's alternating current. So if I've got electrons that are moving like 1 meter a second, but they switch direction 60 times a second, how far would any individual electron ever get in an AC circuit? It's not like the electrons are going to go very far before they alternate and switch back and forth. So what we're going to end up with is an electron gets pushed some direction for a while, and then it gets pushed back in the other direction, and it gets pushed back. To calculate how far an electron might travel in each direction, we could go back and use oscillatory motion equations. So back in chapter 13, 14, something like that, we looked at oscillations, probably chapter 13. And we had worked from these formulas. Now if I put in some kinematic formulas for the electron oscillating in my AC circuit, I could write that as x naught times the sine of omega t. V is equal to V naught cosine omega t. I can get that by taking a derivative. So if I now look at what the V naught would be equal to by taking a derivative here, what it tells me is that V naught is equal to x naught times omega, and that x naught then is V naught times divided by omega. So if I put in a number for my drift velocity, kind of a peak velocity, and divide through by the frequency, that actually would tell me how far in each direction, what's the amplitude of oscillations that are taking place. And when I put those numbers in, the 1 millimeter and the 377 radians per second, now I gave this a boost of square root of 2 because it's a peak velocity, and the number we've calculated we should think of as RMS. So if I think of that as an RMS velocity, creating an RMS current, I'm trying to make sure that we're matching the effects here. Then the number I ended up with was 3.75 micrometers. So you're thinking, really? If I have a light, I turn on a light bulb, and the electrons inside the wiring are only going back a few microns in distance. So it's the very same electrons moving back and forth in that filament that light up the light bulb. They never leave the filament because they just aren't traveling back and forth very far. All right, so kind of an interesting example to think about. I do think it's good to think about the properties of these electrons moving around inside the material. What are the speeds and what are the distances that the electrons travel. Now kind of another interesting example that the book tosses in at the end, and this is again, it's a for your information kind of example. So probably nothing in the homework, nothing on the midterms from this. But we often are told that there's an electrical conduction that takes place in the nervous system, in our brains, in nerves that activate muscles, that these signals are somehow acting electrically. And I do think it's useful to think about what does that really mean. So here's an example of a picture of a neuron. And a neuron has a cell body with a nucleus, but it has these long appendages that stick out in different directions. So it's got these dendrites. Now when the dendrites are activated, signals come in from these dendrites, and they're actually processed within these neurons based on how tight the connections of these dendrites are with the neuron next to it. So kind of all of the cellular processing, information processing in the neurons depends on how these connections are set up. Now the signal travels along this axon, and then it makes connections or synapses with another neuron or maybe a muscle. Now, so there's electrical conduction happening along this. What does that really mean? Well, it's not like a wire. So I always feel like when this is presented and they say neurons act like, it's like the way things are wired, or there's current traveling along the neuron, and I don't think that's necessarily the case. You guys can decide what you think here. So if we look at, into an axon on a neuron, and it says axon right here, physiologically, what your body's doing all the time is it's taking these ions that are in solution, potassium, sodium, chlorine, and it's pumping specifically sodium out from inside. So I think there are these channel proteins that are activated, that are active transport, and they're constantly building up sodium concentrations outside and potassium concentrations inside. So they're just waiting for some kind of a signal to come by. And what they're going to use is they're going to use that concentration gradient that they have generated as a way to transfer the signal. So to me, it's more like a bunch of dominoes. So what's happening here is, here's an axon, or here's a length of neuron, and what happens is they're saying that there's a stimulation that takes place here for some reason. So what happens here is this protein channel opens up. Now what happens is if you've built these concentrations of sodium and potassium, once you open up the channels, the concentration gradient means that on average, sodiums are going to be coming in and potassiums are going to be leaving. Now what that has done is you've set up a condition where you've actually pumped out more sodiums than you've pumped in potassiums. You've generated a charge difference between inside and outside the neuron. And so the stimulation here actually temporarily reverses that. So the ions switch back and forth in this direction. What that does is it opens up adjacent protein channels. Once the charges have switched on the two sides, the protein changes its configuration and it opens up the protein channels that are next to it at the neighbor. So again, I feel like it's more like a dominoes effect where we drop this domino, it hits the neighbors and opens up their channels, opens up adjacent channels. Now it's not like we have current racing down along the axon. What we have is this series of reversals that take place along the axon once we set off one of these protein channels, once we identify a point of stimulation where this charge difference reverses, that sets off a series of events. So if you want to call that electrical conduction, I guess, but that's the idea. Now they're called action potentials, and so the word action potential just refers to this effect of where the protein channels open up and the charges, sodiums come in, potassiums leave. Chlorine ions, I know in that earlier when they showed the chlorine ions too, so it's this balance between kind of the three most common ions, simple ions, elemental ions, physiologically that we have in our cells. All right, this actually may be it. Quick summary, we got a couple minutes here. So for chapter 25, battery gives us electrical potential or voltage. Current is the flow rate of charge, that is what it is. Electrons actually flow whatever direction they're in, the current actually is defined in the opposite direction. resistance formulas and current formulas down below here. And then how do we determine when we're building a resistor depends on the material property of resistivity, the length, and the cross-sectional area. Power is given by IV. That's true for a battery. It's true for a resistor. It's true for a capacitor. If that's a battery, then that's the rate at which energy is coming out of the battery into the circuit. If it's a resistor, it's the rate at which thermal energy is being generated in the resistor. If it's a capacitor, it's the rate at which energy is either being stored or released from the capacitor. So P equals IV, that works on any individual device. Direct current is constant alternating current. We're going to use a sine or a cosine function to represent alternating. When we talk about power and current and voltages in AC circuits, which anytime you plug something into the wall outlet, the values we work in terms of are the RMS values. And they're related to peak values by that 1 over square root of 2, or about 70.7%. And then finally, our formula for drift speed. How is the speed of the electrons related to the amount of current going through a wire? And that's it. So any questions, send them my way. And I guess I'll just stop there. So we'll stop that. That takes us through all of chapter 25. Uh-oh, I got a low battery signal. That was just in time here. All right, take care.